Hello everyone, my name is William, and this is my final video for ENME 49Y. A little bit of background on the project. Our goal here is to do a 3D scan of our target on campus this semester in hopes that Dr. Mitchell will be able to have a 3D scan of the entire campus. So a little bit of a description about my target. I picked a bird statue that is located in front of the Center for Youth in front of Oakland Hall on North Campus. The reason for choosing this target was, one, it was a simple shape, it was relatively small volume, it was about the same height as I am, and there were a couple interesting geometries such as the beak, the round belly of the bird, and the tail that could really come out well inside a 3D point cloud. So just to give a little bit of background on what remote sensing is being able to measure and acquire data on an object without having to physically touch it. So whether it's the temperature, the color, or the distance of the object, remote sensing is being able to sense and measure data without having to have contact with the target you are interested in. Now with remote sensing, there are two kinds of systems which we can see here. There is a passive system and an active system. And in passive system, we use natural radiation or sunlight as the transmitter, and we use the pulses and energy from the sunlight off of the target and acquire that data through our receiver and analyze the data post-processing. In an active remote system, we use our system to actively send and transmit laser waves or other forms of radiation towards our target, and we use that same system to analyze and receive the data. Our project this semester is mainly focused on the principles of LiDAR. LiDAR is laser radar. In a LiDAR system, photons or pulses of laser light are shot towards a target, bounce back off the target, and are received by the same system. Now, from the transmitter, there are a variety of different ways of shooting out the number of photons or laser pulses. This semester we focused on a Gaussian pulse wave. So based off of the return from the target, we can see that the difference between our initial transmission and what we receive in the system will give us information on the distance and the shape of the target we are interested in. Another principle that our project is based on is computer vision. Computer vision is a general term for the ability for software computers to analyze images or videos and record and measure data from various sources. These principles of remote sensing greatly relate to our project. In our project, we are using a red line laser and Raspberry Pi and computer vision in Python to shoot out red laser light towards our target, receive the returns through the Raspberry Pi camera, and do computer vision data analytics through Python and OpenCV. Alright guys, so I'm going to go over my LiDAR setup for ENME 49Y. So we can start off with the transmitter, which is a red line laser here, powered by 5-volt Arduino. Just use some electrical tape to kind of hold down the ends of the ground and the power. And then this is connected to the Raspberry Pi, so the Arduino is powered by the Raspberry Pi through a USB cable. And the Raspberry Pi is also responsible for the receiver, which is an 8 megapixel camera, kind of tied down here through some hair clips. And most of the electronics on this system are held together through rubber bands. I felt that was one of the simplest and quickest ways to kind of hold down all the electronics here. And I kind of had to print the LiDAR system into two pieces, which is why you can see the clips and the tape here, just to kind of reinforce the Gorilla Glue that I put down. I'm going to the power source for the Raspberry Pi through a micro USB cable. It's connected to a power bank, giving off roughly 5 volts and 2.4 amps of current, which is approximately what the outlet cable would normally give the Raspberry Pi. And here we have a standard camera tripod, kind of holding together with a mount, and that's also tied down by a couple of rubber bands and overlaying them one on top of And in order to kind of use Python software on the laptop and kind of communicate with the Raspberry Pi, we have an Ethernet cable here, which connects to my laptop, so I can use the Raspberry Pi remotely through VCN software. And so just going over the basic layout of the LiDAR again, so the red line laser acts as a transmitter, sends out photons to an object, and the photons come back and are received by this camera. And that camera takes the data and inputs it into the software of Raspberry Pi, which we're using Python for this class. And we can do a variety of things with the camera images and the pixels that we receive and kind of manipulate the data from there. Now we're going to go through the sensor calibration and testing, and so you can see two configurations here. The one on the left is a single laser, and the one on the right is with the LiDAR setup. Since we have our laser and camera 12 inches away, there's a certain plot that the LiDAR system has to follow in terms of the placement of the pixels in the image and the distance from the object to the LiDAR system. So as you can see here, we're going through a montage of videos. The first was the single line laser and moving 6 inches apart from a wall up to 10 feet. And this is the LiDAR setup, doing the same process of moving away from the wall, 0 to 10 feet in increments of 6 inches. Alright guys, so we're heading into our second part of the scan phase. So as you can see, I'm coming from another angle. In the first segment, we scanned the bird from the front, got our first preliminary scan, and now I'm continuing to scan the bird from 3 other sides. So we have the bird's right side on the left, around this area, about like 7 to 10 feet from the bird, and the final angle from the back about here. Some of the challenges with this shape, and especially this environment, there's a lot of ambient lighting here. We actually had a light here that I'm covering with a cardboard box now, to kind of get rid of some of the noise, and unfortunately there's nothing I can do about the parking lot lights as well. So a lot of filtering needs to be done on these sides. Alright guys, so just another note, I ended up having to put a bunch of paper and tape along the bird just to get some better readings. Some of the coloring on the backside of the bird was a little bit too dark and kind of forced me to take other measures to get a little bit better data. With the dark spots on the bird, a lot of the red laser was not coming off of the bird very well, and the dark... Hello everyone, we are now going to go through the final stitching process for my target this semester. I went back out on campus and recorded 3 other sides of my bird, and I uploaded the JPEG files to my email and downloaded them to my computer. I then uploaded the JPEG files into PyCharm and used the color picker code to go through the HSV filter and kind of find a sweet spot for the filter's min-max to kind of get rid of all the ambient noise within each picture. And as you can see, we get a clean image of just the red line laser within the frame. So now we go to the data generation code and input those HSV values into the code. And we will run it for the back side of the bird, and so you can see the final XYZ coordinates from each picture here. And using the text file that PyCharm outputs, I uploaded this to MATLAB and graphed that same XYZ plot. And I did this for all sides of the bird, so I mapped the front side, the back side, the right side, and the left side. And I made sure, after mapping all of these XYZ coordinates, I made sure that they were all at the origin of each plot. So when I stitched the separate XYZ plots together, they would come together nicely and each side would correspond to each code. And you can see in the final code here, I basically copy and pasted all 4 codes into one MATLAB file and plotted all the XYZ coordinates at one time. As you can see, we have the beak and head and belly of the bird and the stone that it's sitting on, as well as the wings flapped on the back. I think the final scan turned out pretty well given the ambient lighting, although there is a little bit of noise. Alright everyone, we're going to go through the final mesh now of my target this semester. Just as a reminder, I scanned the bird in front of the daycare by Oakland. And so here I'm just going through the MATLAB code again with the final point cloud. I'm showing the different text files that I have to put together for the final mesh. So I combined all the text files I had in MATLAB after they were transformed and put them all into one file called Final Bird Cloud. And this is the text file I imported in the Mesh Lab. And here we have a couple of examples and iterations of me trying to perfect the mesh of the bird. As you can see, this first one has some defects that I had to cut out. And the second iteration here is a little bit better, but there's still some holes and the surface is a little bit rough on the bird. And here is the final mesh here that gave me the best results. And I'll take you through a demonstration right after this to show how I achieved this result. So first I start a new project and import the text file with all of the XYZ coordinates of the final point cloud. And here I'm just doing some cleaning up and deleting all the noise points within the 3D point cloud before I start the mesh process. Alright, so now we're going to head through the different commands, and so first we show the normals and then compute the normals for point sets. And so here, through most of the iterations, I found that the best method was to flip the normals and set the neighbor num to 250 and have the viewpoint position at 0020 with the trackball center. This kept most of the normal vectors pointing inwards to the center of gravity of the bird. Next, for the Poisson surface mesh reconstruction, I found that the best results occurred when I set the depth to 11. Besides that, there were no other changes made to the default settings. And after this, I did a little bit extra manipulation with the mesh and did a Laplacian smooth. I found that this kind of compressed the mesh a little bit to kind of fit more of the form of the target, and so it kind of gets rid of the little blobs here and there that appear on the mesh due to extra noise. And as you can see, the final mesh looks pretty good. You can see the curvature of the bird, the belly, and as you can see, we still have a little bit extra faces on the bottom platform, so I just go ahead and manually delete some of the faces input by MeshLab here. And after deleting these faces, this is pretty much my final mesh for my bird.